Good morning, everyone. Today, our group FantasticFive, we would like to present our case study titled Traffic Congestion Avoidance Routing Simulation System. Our project focuses on simulating congestion-aware routing to reduce traffic pressure in urban areas, especially Ho Chi Minh City. So let's begin by briefly introducing the background and the motivation behind our project. In many cases, even when a road is congested, users are still routed through it by Google Maps. In this presentation, we will cover 5 main parts: the problem, the objective, the target user, the scope, and finally the algorithms and system design we apply. So, popular navigation apps today focuses on users' optimal routing. This means they usually direct users to the single faceted route. While this works for individual drivers, it unintentionally increases the pressure on major roads, leading to congestion. By that, our objective is to propose 1 to 2 optimal alternative routes that can bypass simulated congestion points while still remaining practical in terms of distance and travel time. So our primary users include individual drivers, logistic and delivery companies, especially those operating in congested urban environments. Our study focuses on the key intersections and corridors around Cộng Hòa, Trường Trinh, and Lý Thường Kiệt streets. These areas are well known for congestion hotspot in Ho Chi Minh City. To solve the problem, we use Dijkstra algorithm combined with a bit penalty mechanism based on the PPR traffic modeling. Next, we analyze the problem in more details and explain our solution approach. The core problem is simple to state but difficult to solve. How can we find the optimal route from point A to point B in a road network that contains congestion points? Existing navigation apps such as Google Maps, Apple Maps, and Waze are highly effective at reacting to traffic in real time and optimizing long routes. However, they also have notable drawbacks. When all users are directed to the same faceted route, congestion becomes unavoidable. Some apps are also overly sensitive to shortcuts or narrow streets. From users' perspectives, we identify several key pain points. First, navigation apps often find the shortest routes, but so does everyone else. Second, they react to congestion, but they do not help prevent congestion before it happens. And last but not least, they tend to ignore real-world travel costs, such as fuel consumption or stop-and-go traffic. These problems leads us to our how might we questions. How might we discover multiple optimal alternative routes? Or how might we enable proactive routing, allowing users to mark the congestion points they want to avoid? Or how might we optimize travel on clear roads, not just on shorted paths? In reality, local drivers often avoid congestion by using alleys or detours. While this behavior is effective, the information is scattered and informal, making it difficult to integrate into navigation systems. As a result, many drivers still end up on crowded roads. You can see from the videos I'll show on the slide. To validate the importance of this problem, we refer to TomTom traffic index data from 2024. In Ho Chi Minh City, the average congestion level is 30%. The peak hour congestion reaches 64%, and drivers waste approximately 96 hours per year in traffic congestion, which equals to 4 days. Now, let's move on to our technical method. We model the road network as a weighted graph. The nodes represent intersections. The edges represent road segments or junctions. The edge weights represent travel time, not just distance. And importantly, these weights are dynamic changing with congestion. Our system uses two graphs. The main graph is a directed graph with dynamic BPR weights used directly for route finding. The second one is the congestion graph, which is undirected and stores vehicle counts only. It is used for data storage and synchronization, not routing. Well, this is a paper that our groups collect. This supports our choice of the penalty method, as it shows that penalty-based routing achieves higher route diversity and user satisfaction compared to single optimal approaches, particularly in urban road networks. Based on prior research, we chose the penalty method because it consistently achieves higher overall routing quality compared to traditional shortest path approaches. The literature shows that penalty-based routing is particularly effective for short urban routes, where alternative paths through secondary roads or alleys are feasible. So by incrementally increasing edge weights after each selected route, the method encourages that route diversity while still maintaining efficiency. This behavior aligns well with real-world driving patterns in dense city, which explains why the penalty method outperformed Google Maps in our evaluation, especially for small route scenarios. This method is computed using BPR formula, where parameters such as alpha, beta, and capacity can be adjusted by regions. This allows us to simulate realistic congestion behavior. The system finds the nearest ramp nodes for the start and end points, computes the shortest path, updates congestion data, and finally extracts edge geometry for visualization. And now this is a live demo of our solution. Please check it out on your own.
Thì bây giờ em sẽ thử chạy code cho mấy thầy xem. Thì cách chạy thì các thầy cứ git clone code trên GitHub về, sau đó thầy cd vào cái thư mục SmartFlow, sau đó thì chạy cái lệnh python app.py, nó sẽ sinh ra một cái link localhost, rồi đó mình cứ click vào link localhost này. Ở đây em giả sử em test cái đoạn này thì ví dụ như mình chế độ tìm đường thì mình click 2 điểm, sau đó nó sẽ chỉ ra cái đường từ điểm A đến điểm B. Giả sử bây giờ mình muốn lock cái đường lại đi thì mình sẽ chọn 2 điểm đi, sau đó mình enter thì mình sẽ lock cái đường này lại. Sau đó thì mình tiếp tục mình tìm đường đi, thì nó sẽ chỉ ra một cái đường khác với cái thời gian là 1 phút và nó trên là so với cái đường payline là 463 m. Giả sử như mình muốn tiếp tục mình muốn lock cái đường này lại, ví dụ như cái đường này nó kẹt đi Thì mình cũng tiếp tục mình click cái điểm ở đây, sau đó mình enter. Rồi bây giờ mình nhấn tìm đường. Thì ở đây cái yêu cầu của mình là mình đang muốn cái độ là tối đa của nó là 500 m thôi. Giả sử tôi chấp nhận là tôi cho cái độ là nó lên 1000 m đi, thì để thử xem nó có ra tìm đường khác hay không. Thì ở đây nó sẽ chỉ một cái đường khác với cái độ lệch khoảng 1 km so với cái đường ban đầu, đường bay lai.
Our target users include daily commuters, delivery and logistic drivers, drivers familiar with local roads, or traffic researchers and planners. To evaluate our system, we compared it against Google Maps using standardized metrics. We evaluated the system across 4 dimensions: routing quality, performance, BPR accuracy, and user experience. All metrics are grounded in scientific literature and industry standards. To ensure the reliability of our evaluation, we designed a structured and statistically routed test suite. We conducted experiments on a sample size of 30 routing cases, which is considered the minimum sample size for statistical validation in experimental design, ensuring a 95% confidence level. The test set was evenly distributed across 10 short routes, 10 medium routes, and 10 long routes. Each route was tested under 4 traffic scenarios: free flow, light congestion, moderate congestion, and heavy congestion. We also varied travel directions to avoid directional bias, including north to south, east to west, and diagonal movements. With a sample size of 30, the margin of error is approximately greater or less than 18%, which is acceptable for a system-level simulation study, as referenced in Montgomery 2017, Design and Analysis of Experiments. Routing quality is the core performance indicator of our system. So, we evaluate it by using 3 scientifically established metrics. The first one is route diversity, measured using the check-S distance, which evaluates how different 2 routes are. A lower overlap means higher diversity. Our target threshold was greater than 0.3, but which is commonly used in route diversification research. The actual result was 0.416, indicating that the generated routes are meaningfully different and not minor variations of the same path. The second metric is route efficiency, which compares the actual route length to the theoretical shortest path. According to Wardrop's user equilibrium principle, efficient alternative routes should not significantly deviate from the shortest path. Our target was greater than 0.95, and the system achieved an actual value of 0.996, meaning that the alternative routes remain highly efficient despite avoiding congestion. The last metric measures how effectively the system avoids the congested road segments. Our target success rate was above 0.85. The system achieved an actual avoidance rate of 1.0, meaning that all suggested routes successfully bypassed blocked or congested edges in the test scenarios. In addition to routing quality, we evaluated system responsiveness, which is critical for real-world usability. Each test case was executed 5 times, and we recorded the average response time, the minimum response time, and the maximum response time. The system consistently responded in under 2 seconds. According to usability standards, under 2 seconds it's rated excellent. Under 3 seconds is considered good, and over 10 seconds is considered unacceptable. Therefore, our system achieves an excellent performance rating. We also evaluated the accuracy of our traffic prediction model based on the Bureau of Public Roads (BPR) formula. Compared to the standard parameters, the standard alpha is 0.15 and the beta is 4. We increased the beta to 8 and the alpha to 1.5. Our parameters were intentionally chosen to increase sensitivity to congestion in dense urban environments. The model accuracy was measured using mean absolute error (MAE). The system achieved an MAE of 0.415, which is higher than the ideal target of below 0.2. This indicates that the model currently overestimates travel time under heavy congestion, which is a no limitation and a focus for future improvement. Based on ISO standards and cognitive load theory, our system achieved an overall UX score of 90.3 out of 100, indicating strong usability and route acceptability. Finally, we aggregated all evaluation dimensions into a weighted score. Routing quality 40%, system performance 30%, PBR accuracy 20%, and user experience 10%. The final overall score is 85 out of 100, corresponding to a grade A, very good. This confirms that the system performs strongly in routing effectiveness and usability while leaving room for improvement in traffic prediction accuracy. Based on our evaluation, we propose 3 main directions for future development. The first one is advanced route topology. The current Planet RAP model struggles with complex interchanges, such as flyovers and overpasses. We propose implementing a multi-layer 3D RAF, which can accurately represent vertical road structures. The second one is predictive model refinement. Since the PBR model overestimates travel time in heavy congestion, future work will focus on data-driven tuning of alpha and beta parameters to reduce MAE below 0.2. And the last one is scalability and real-time data. To scale the system citywide, we plan to integrate real-time GPS feedback, enabling dynamic weight updates and more realistic congestion modeling. So that's the end of our presentation. Thanks for listening.